SwayamPrabha. Digital India. Educated India.
Okay, so welcome back to one more lecture on Introduction to Soft Matter. And last time, so in the lab we had a very nice session where we took a look at actual rheological characterization of some of these fluids, and we took a look at how these fluids can be, so how some of the theoretical constructs that we discussed early on in the class, how that looks like in a real experimental situation. And some of the things that you probably noticed is that there was noise, the curves are not as well behaved obviously as we are drawing it in the theoretical setting. At the same time, the idea of linearity, which seemed most likely would have felt to you that must be valid in many cases, seemed quite not so applicable in at least one of the cases that we saw. But those experiments you have to do multiple times. It has to be repeated, which we did not do for the interest of time. You can also use different geometries to study the same rheological characteristics. We did not discuss that because this is an introductory course, and in that introductory course we are not delving into all the details. So if you take a more advanced course, those are some things that you would get to understand. But now that we have taken a look at the relaxation phenomena, we want to ask ourselves as to what are some of the simple models which can give us elementary relaxation behavior, right? And before we go, so we will look at a model known as Maxwell's model. We will also look into the original paper in which Maxwell offered this model to us. But before we do that, we want to take a quick look at a couple of important topics, which are the Lagrangian and Eulerian perspectives. There is an important reason why I am discussing this, and it is often not clear in many of the textbooks when they derive the Maxwell's model as to what is the basis for application. So we want to make sure that our case is well understood. So let us discuss these two important perspectives. Now, Lagrangian and Eulerian perspectives are two perspectives by which you can observe or explain deformation of a material or a flow, right? And these are two perspectives which are based on the person who is observing the flow. Okay. And so these two common ways to study a moving fluid or a deforming body. So the first is the Eulerian one. In the Eulerian one, what we do is we look at a particular location and then we observe how all the particles or how all the material points are flowing through that location and how that behaves. Okay. So here what we do is we look at a particular location and observe. Okay, so this is O, sorry, looks like and observe how all the fluid passing through that location behaves. Okay, this is the Eulerian point of view. So, what do we mean here? We mean that in this condition we will create, let us say you will create a mesh and these meshes are static, okay, and you have all the different particles. So, these are fluid particles and these fluid particles all have a velocity and they are moving in different directions. Now, instead of observing the individual fluid particles, you say that I will confine my attention to this particular window. So, let us just say this particular window, I am just taking an example, and then you will say that okay, I will look at all the different fluid particles behaving how they behave as they pass through this. But once they pass out of this control window of this section, I will not bother, then it is to be studied in the next control window perhaps, right. So, I will only confine my attention to this small section and you can probably realize that this is your control volume. And if you take this same control volume and then you say that in the limit of the size as it shrinks down to 0, that will also become your differential control volume, right. So, this is the Eulerian perspective where you do not track individual fluid particles, but rather say that the way I am going to look at it, I am not going to bother about all the different fluid particles, rather I will keep my view fixated on certain meshes or grids, and these grids are your control volume and I will quantify the behavior in these grids. Okay. So, this was one. So, the second one is the Lagrangian perspective where you look at a particular piece of the fluid, a fluid packet. Okay. So, in bracket you can put a fluid packet and observe how it behaves as it moves from location to location. This is your called your Lagrangian point of view. So, what do you do here? Let us say you have a fluid particle and let us say it is possible for you to identify that particle. Okay. So, how you identify that I am not discussing that, but let us say somehow you are able to identify this particular particle and this particular particle is now going to move through these different locations at different times and this is your path of that. So, this is let us say at some time t naught. So, this is some t naught plus delta t. So, this is your initial position. So, your position now, the position vector is a function of your time, right. So, this is your Lagrangian point of view where you are looking at individual fluid particles and you are following them. So, why are we discussing these two, by the way? Why is this important? Well, because when you apply Newton's laws, they are applicable for a fluid particle when you are looking at it from the Lagrangian perspective, right. So, Newton's laws are applicable to this mass as it moves through, but it may not be, it is not applicable in the same way in its original form to this control volume. So, for application to the control volume we have to do something different. Right. So, the difference is in the Lagrangian point of view is that, for example, if you have the position vector, that is just simply a function of time here, right. As the position vector value itself is changing just as a function of time. Whereas, if you are looking from the Eulerian point of view, then, and let us say you are tracking the velocity field in a differential control volume, then your velocity vector is, so your u is now a function of your time as well as x bar, which where x bar is now the control volume location, right. So, when you apply the derivative, if you want to apply the derivative, you want to apply it such that the derivative with respect to time is following a fluid particle. And if you are looking at it from the Eulerian perspective, so if u is an Eulerian variable, you cannot compute this time derivative easily. So, for that what you have to do is, now it is a there are two variables here, right. So, you have to individually take derivatives, and by the chain rule you will know that you will your derivative will look something like this. So, I am just applying the chain rule here, okay, because here to evaluate this was not, to evaluate this I must apply the chain rule and look at it from that perspective. Now, you will notice that in the case of the Eulerian system, these are nothing but your Eulerian velocities. Okay. So, that is why you have the concept of, when you take the Eulerian derivative, in the Eulerian sense you have to take a material derivative, and that is usually a derivative of this form, right. So, I am saying, when you have to, if this is an Eulerian variable, then when you take the derivative following a particle, you have to take it in this particular form, and this can be any quantity, it can be a scalar, it can be a vector, and right. Okay. So, with that small introduction, we are now ready to discuss constitutive relationships. Okay. So, what we want to do now is we want to look at constitutive equations for 1D response of viscoelastic materials. Okay. And to do that, now we had discussed some time ago, just scrolling through the notes to find where we had discussed that. Okay. So, we had discussed some time ago that 1D response can be interpreted as a combination of elastic and viscous responses, right. This is something that we had said long ago when we had discussed what a viscoelastic phenomena is, right. So, we are just saying that in the case of 1D material 1D response, we can obviously go back to that idea where the viscoelasticity is represented as a combination of elastic response and a viscous response, right. So, let us say take the case of elastic the body. We had just said that there was one analog that we can use, and that analog allows us to interpret or model elastic response, and that analog was your spring, right. So, your spring represents energy storage, and your dashpot, this represents energy dissipation. Right. By system to the surroundings. So, that will help us create this first and the simplest of the viscoelastic models, where what we will do is we will put them in series. Okay. But before we go here, as we have been doing frequently in this course, whenever we introduce an interesting and important topic, we try to see if we can go back and look at the original works where this was represented. So, this is the manuscript by James Clerk Maxwell, which is titled On the Dynamical Theory of Gases. It was published in 1866, and this is the manuscript where he proposes the Maxwell's model. The history of why he was trying to look into the dynamical behavior of gases is an interesting something you can look up later on by itself, but we are not going to concern ourselves with that. So, in the beginning he talks about the theories of the constitutions of bodies, and if you know, at that time they had still not seen an atom. Right. This is 1866. This is still before we have been able to image an atom, and we have been conclusively able to prove that materials exist as atoms and molecules. So, this is predating that time, but there are different philosophical there are people who had sort of guessed that material is going to be made out of small particles. So, in the beginning he talks about that, and that is quite interesting to read, because he says that the theories of the constitution of bodies suppose them either to be continuous and homogeneous or to be composed of a finite number of distinct particles or molecules. So, he is talking about the two ways in which we believe that the material exists. So, the first is the continuum model, where the continuum case where the material is just believed to be homogeneous at any scale, even if you go down smaller and smaller, and in the other case it is always supposed to be composed of a finite number of particles or molecules. And then he goes over the different ideas that are prevalent at that time, says that if we adopt a statical theory and suppose the molecules of a body kept at rest in their positions of equilibrium by action of forces in the directions of the lines joining their centers, we may determine the mechanical properties of a body so constructed if distorted, so that the displacement of each molecule is a function of its coordinates when in equilibrium. So, he is saying that if you knew the internal forces, then you would be able to figure out how the body is going to react to that, right. So, this is something that you can read at your leisure. It is downloadable. It is also available on arXiv. I believe one of the arXiv platforms has all of Maxwell's papers. There is even a section where he goes into the ideas where, so some of this I had referred to in one of the earlier classes, that the opinion of the observed properties of visible bodies apparently at rest are due to the action of invisible molecules in rapid motion is to be found in Lucretus. So, he is referring to the Roman and the Greek literature on the idea that matter is composed of small indivisible parts. And we know that there was a similar school of belief in India at that time, which was called the Vaisheshika system, of which Kanad is probably the most well known propounder, which also believed that the materials are all composed of small atoms and molecules. So, he goes through all that, and then he introduces this particular equation, where there is a solid body. So, there is a solid body that has, so dF by dt equal to E times of ds by dt minus f times of t, where there is a body which has both elasticity and viscosity at the same time. Right. So, this t is a relaxation time scale. So, we will go down, what we will do is we will try to derive this from our first principles, and we will see whether we end up using this, we end up with this equation or not. Okay. So, let us go back to the Maxwell's model. So, here we said what we are going to do is we are going to put into series, and let us say this is represented by E and the modulus here, and this represents the viscosity of eta. So, the viscosity and the E are constants, and you are applying a force, and as a result both the spring and the dashpot will experience some displacement. So, let us say that the displacement observed here is delta x s, the subscript s standing for spring, and the displacement by the dashpot is delta x d, d being a subscript for dashpot, right. And these themselves are massless. Okay. So, we will also make a note that these are massless. So, now the total displacement in the system is, so let us say that this spring dashpot combination is representing a Lagrangian material point. Okay. So, now if that is the case, then what we want to do is we want to apply force balance, and we want to see where that leads us to. But before we do that, then let us quickly write that from geometry of the current system, the total displacement in the body is equal to delta x s plus delta x d. We want to apply force balance. So, consider these as separate entities. Okay. So, I am just going to create a separate pane here and draw that. So, if the force applied is F, then my force balance on the system requires me, and since these are massless, that the forces on both sides will be F t for the spring, and similarly for the dashpot. Right. So, if I were to write the from force balance, we have Ft, or the force Ft is equal to Fs right, where Fs is the force being experienced by the spring and Fd is the force that is being expressed by the dashpot. Okay. And our question that we want to answer is we have to find a relationship. So, the question is find a relationship between delta x and Ft. Okay. So, this is where we are trying to get. Okay. So, now what do we know about Fs and Ft? So, Fs we know is the force that is in the spring, right. So, if that is the force in the spring, then from our analogy the relationship between the force and the displacement in the spring should be this, because this is a linear spring, and the force in the dashpot should be okay. So, what we will do is we will stop here today, and the next class we will take out from here and we will try to derive the formula.